Precision demolition is not about brute force. It relies entirely on controlling stress wave propagation. High explosives generate supersonic shock waves characterized by the detonation velocity, or VOD, which typically ranges from 3,000 to 9,000 meters per second. Brisance quantifies the shattering effect of the explosive, a critical factor for severing high-strength materials like reinforced concrete columns. The initial shock wave creates compressive failure within the material. This compression is immediately followed by a tensile reflection wave that maximizes material fracture precisely at the charge interface. Controlling the VOD ensures the energy release is perfectly synchronized with the structural failure timeline. Engineers must calculate the impedance mismatch between the explosive and the target material to maximize energy transfer efficiency. This precise control dictates whether a structure collapses or merely sustains damage. Demolition engineers select explosives based on required brisance and thermal stability. Plastic explosives such as C4, which is RDX-based, or sheet explosives, which are PETN-based, are commonly used due to their high VOD and moldability around structural members. Linear-shaped charges, or LSCs, are essential for cutting thick steel members, utilizing the Monroe effect to focus detonation energy. The LSC liner, often composed of copper or steel, forms a high-velocity jet capable of severing thick steel beams with minimal peripheral damage. Charge placement requires calculating the critical diameter of the structural element. This calculation ensures complete severance is achieved using the minimal necessary explosive mass, optimizing safety and cost. Pre-demolition structural analysis identifies all primary load-bearing elements, including critical columns and shear walls. Simultaneous removal of these elements initiates the controlled collapse sequence. Engineers must calculate the structural redundancy factor. Highly redundant structures require significantly more extensive charge placement to ensure complete failure initiation. The analysis precisely determines the exact location and orientation of charges to create a controlled, progressive failure path. The objective is to ensure the structure falls vertically within its established footprint. This vertical trajectory is achieved by removing supports in a calculated sequence, which actively prevents uncontrolled lateral movement and minimizes the debris field. Precision collapse relies entirely on millisecond delay detonators to orchestrate the exact structural failure sequence. Timing sequences are calculated to ensure the upper floors exert maximum vertical load onto the failing lower sections, maximizing the conversion of gravitational potential energy. Delays typically range from 25 milliseconds to 500 milliseconds between different floors or distinct structural sections. This sequential removal creates a calculated hinge effect, causing the structure to buckle inward and significantly minimizing the lateral throw of debris. The timing sequence must accurately account for the structural's natural frequency of vibration. Furthermore, the speed of sound through the specific structural materials must be factored into the delay calculations to ensure simultaneous failure initiation across wide elements. Safety engineering mandates strict control over external effects, primarily ground vibration and air overpressure. Ground vibration is continuously monitored using sensitive seismographs. Engineers ensure the peak particle velocity, or PPV, remains below regulatory limits. These limits are typically 50 millimeters per second for infrastructure and significantly lower near sensitive residential areas. Debris containment involves wrapping charged columns with specialized geotextile fabric and heavy chain-link fencing. This wrapping absorbs fragmentation energy and effectively prevents the high-velocity throw of shrapnel. Air overpressure, which is the blast wave, is mitigated by careful charge burial, a technique known as stemming, and by minimizing all exposed explosive surfaces. Proper stemming ensures maximum energy is directed into the structural member rather than into the surrounding atmosphere. For smaller structures, home building sites, or sensitive urban environments, non-explosive methods are often preferred over traditional implosion. Chemical expansive agents, known technically as soundless cracking agents, are poured into pre-drilled holes. These agents hydrate and generate internal pressure exceeding 100 megapascals over several hours. This process fractures concrete silently without generating noise or external vibration. Mechanical methods such as hydraulic bursting or diamond wire cutting offer precise section removal for infrastructure components like bridge decks or foundations. These methods eliminate the need for extensive blast permits and the establishment of large exclusion zones, streamlining operations in densely populated areas. Demolition planning scales significantly based on the structure type and proximity constraints. Residential structures, typically wood frame or light commercial, rarely utilize explosives. Mechanical methods such as high-reach excavators are standard due to tight lot lines and minimal structural mass. High-rise implosion requires extensive geotechnical surveys to accurately predict ground response. It also demands detailed modeling of the final debris pile height and spread. The primary engineering difference is the energy management required. High-rise implosion converts massive gravitational potential energy into controlled kinetic energy within a defined boundary. This complex energy conversion factor is entirely irrelevant in typical residential deconstruction projects. The future of demolition integrates advanced technology to enhance precision and maximize material recovery. Building information modeling, or BIM data, is used to simulate collapse dynamics with extremely high fidelity. This simulation optimizes charge placement and refines timing sequences in virtual environments before physical execution. Robotic systems are increasingly deployed for charge placement in hazardous or structurally unstable buildings. This deployment significantly improves worker safety margins by removing personnel from high-risk zones. The industry trend emphasizes deconstruction, which means maximizing material recovery, and recycling, which requires cleaner, more segmented structural failure than traditional, less controlled demolition methods.